So number 31 is very reminiscent. I think. I think number 31 was very quick. I'm not sure why. I know G is a group. What does that mean? I know the three properties and the cancellation rule. I'm just listing them up there for my own, so I know them. And I have to show there exists exactly one idempotent element. Well, I know there's one. E is idempotent, right? E squared is E. So that one's done. So I assume that there's another one, two idempotent elements. X squared equals X and Y squared equals Y. Goal is to show X equals Y. Well, I didn't get very far because my scratch, when I started playing around, I get X equals E right away. So there was nothing to do. So I lined everything up and it was kind of like boring. So here's my clean proof. Let G be a group. We will show that G has exactly one idempotent element. And first we will show that there's at least one. Ta-da! Y equals E. Then by definition of identity, Y squared is equal to E star E, which is E. This means Y squared equals Y. It's idempotent. Now assume X star X equals X for some other X. By the cancellation law, blah, blah, blah. Not a very interesting proof. This is one of the proofs where you think, did I do something wrong? Why is this number 31? This should be number 29. The other one should be number 31. And the final proof. Let G be a group with finite number of elements. Show that for any A in G, there exists an n in positive integers such that A to the n is equal to E. So if you decide to do a master's thesis in games, you'll find in a lot of games you only have a finite number of moves, and eventually you're going to have that a combination of moves ends up being the identity. That's why the Rubik's Cube works, right? Eventually you have to end up back at the identity because there's only a finite number of moves. It might take you a long time to get there, but really that's the end story, right? So that's instrumental in that proof. There's another thing that I worked on called NIM games, and in that case also we have recursions, and we have only a finite number of things that are possible, and so you can start using this kind of an idea. So what do we know? Well, we know this one I didn't list out the null in the show, and probably because I've seen it so many times and it's so important. So I'm going to label all the elements of G, which I can because it's finite. It ends at some point. I can do this. Notice that I flagged the hypothesis. I say I can do this because by hypothesis G is a finite group. And consider the element x1. I could choose any one of them. Eventually x1 to the k must be something I've seen before. Why? Well, if it was something different every single time I raise it to a power, well, I'm going to run out of things. So it can't be something totally different. Eventually it's got to be something I've already seen before, because I would have run out. There's the finiteness. That is that I don't have here infinite sat. I can't just keep going. So x1 squared can't be something different. Eventually I was going to have to stop being something different because I only have a finite number of elements to run through, and by closure I don't go out of the set. So eventually there's going to be a power k where it's something that I've already hit a power of before. Well, now I just use the cancellation law. I just keep applying the inverses to both sides, and I get, because I just pick the smaller of the two and I just apply the inverse that many times, and eventually if I choose my n to be k minus j, I get x1 to the n is equal to e. So I have all the little computations there, scratch. Since n was something positive, x1 to the n is equal to e for some n belonging to the positive integers. But I chose x1 arbitrarily, so this argument holds for any of those. I could have picked x2 or x3 there. It's the same calculations. So a to the n is equal to e for some n. And I didn't go and elaborate on that one. I've seen it so many times. It was on my comprehensive exams, and not in this form, but some other form. I think they asked something about matrices. So, are there any questions about proofs or how to write these up or how they work? Remember what von Neumann says, you just get used to it. You don't really learn it. No questions?